My name is Christina Pepper. I'm from New York University, Abu Dhabi, and it is my pleasure to present our work, Trust the Crowd, Wireless Witnessing to Detect Attacks on ADS-B-based Air Traffic Surveillance today. This is a joint work with Kai Janssen from Ruhr University Bochum, as well as Liang Niu and Yan Shu from my group in Abu Dhabi, as well as Ivan Martinovic from the University of Oxford. Kai has worked long and hard times on this paper. He has, in the meantime, graduated with a PhD some while ago, and it is my pleasure and my honor to present this paper on his behalf. And credits go to him as well for working on the slides. Let me start with a quote from the International Civil Aviation Organization that acknowledges that civil aviation is mainly reliant on cyber-enabled technology that increases the safety and efficiency of air transport. At the same time, it is also aware that this creates new risks to emerge. We have seen evidence of this in recent years on academic cybersecurity, with papers appearing such as wireless attacks on aircraft instrument landing systems at Usenet Security, with leveraging crowdsourcing to detect and localize GPS spoofing attacks, as well as a view from the cockpit that explores pilot reactions to attacks on avionics systems, as was published at NDSS last year. Our work continues research in this area. We focus on the automatic dependent surveillance broadcast system that has been widely adopted as the de facto standard for air traffic surveillance as of last year. ADS-B-capable transmitters periodically broadcast status reports that inform other aircraft, as well as ADS-B sensors on ground, about their own identities, about position and movement data, and additional status codes. ADS-B reception equipment has become low cost, consisting of an antenna, of cables, and a software-defined radio. A number of flight tracking services exist. Here I show an example from the commercial flight radar system that shows cargo flights on a day in early February this year. The OpenSky network is available to the research community, and here I show data from commercial airplanes from last year, actually, from 2020, before the pandemic started. We do use the OpenSky network as data in our evaluations, and I just want to note here that the OpenSky network has a geographical focus on Europe, but it also covers some other parts of the world. On a typical pre-pandemic day, here the data is shown from February 15, 2020, typically between 100 and several thousands of ADS-B messages are received per location. And for large geographic areas, there is quite some redundancy on the number of sensors that record the same ADS-B message. So on the right-hand side in the figure here, we see that there are typically, for large geographic areas, between 4 and up to more than 10 sensors that do obtain the same ADS-B messages that are sent out by aircraft. And we do leverage this redundancy in our proposal. We use the data of this specific day that is shown here as baseline for our experimental work. Our system model is as follows. We use a kind of straightforward system, so we have GPS satellites that transmit GPS signals. Those signals are recorded by aircraft that then transmit ADS-B messages that contain GPS-derived location information. And they send these ADS-B messages to sensors on the ground that forward their collected data to a central server. Attack equipment has become widely available nowadays. Shown here is an example of a software-defined radio transceiver whose firmware allows to receive, to decode, and to retransmit a whole set of wireless protocols, among them ADS-B as well as GPS. For legal compliance reasons, we do not make use of such a device in our experimental work, but instead we investigate and use attack simulations that allow us to parameterize the attacks and to understand better their impact and the detection probabilities. In particular, we consider 3 attack simulation scenarios. The first one is GPS spoofing, where the GPS signals indicate a deviation from a track from the itinerary that an aircraft is taking by a certain angle alpha. Second, we consider ADS-B spoofing attacks, where ADS-B signals are tampered with. They impact either a single receiver or a set of multiple receivers, or can affect all receivers within a certain geographic area. And third, we finally also consider sensor control, by which the attacker sends messages from attacker-controlled sensors to the central server. So our attacks consider all 3 layers of our system model. Regarding the focus of our work, what do we build is, our idea was to build a trust evaluation process that determines the trustworthiness of received unauthenticated and unprotected ADS-B messages in terms of a score value. So we derive score values for the received ADS-B messages. The content of received messages is first used for a variety of checks. Sanity checks filter out unrealistic maximal heights or unrealistic velocities that aircraft might report. Differential checks filter then out the unrealistic maximal changes relating to accelerations, for example. And dependency checks take into account physical restrictions. So, for example, we compare the aircraft altitude that is reported on the ADS-B messages with the aircraft on ground flag. Second, and beyond these rather standard checks, we take metadata and the crowdsourced knowledge of all ADS-B sensors that are contributing to the system into account. And this allows us to perform cross-checks whether consistent messages were received at an expected set of locations. If any of these 4 different types of attacks fail to indicate an attack, then we perform an attack analysis to determine the type of attack that is happening and to identify affected sensors. This can be done in real time. For the rest of this talk, I will focus on the more interesting case of cross-checks and the verification based on crowdsourcing. So I will focus on the metadata information. And the core of our approach is what we call wireless witnessing, that describes the collaborative process of observing the status of a distributed wireless system. So the question that we ask is an observed ADS-B message with a claimed aircraft ID, is it real? Does it come from a real aircraft that sent this message? If the majority of sensors has received a consistent view of this message, then the answer is probably yes, that's a real message from a real aircraft. Otherwise, the answer is likely probably no, an indication of an attack. So based on the real-world data set from the OpenSky network that I described, as well as our attack simulations of the 3 different types of attacks that we consider, we created a labeled reception pattern set and used that as input to machine learning-based classification system. As machine learning techniques, it turned out that we could focus on decision trees to yield the best results. Regarding our obtained results, let me focus on GPS spoofing and ADS-B spoofing in this presentation. For the detection of GPS spoofing attacks, we considered deviations from the aircraft track with degrees between 1 and 45 degrees of track from the aircraft itinerary, as well as we used a sliding window approach as a compensation, as an approach to compensate for false alarms that may be based on single, possibly misclassified messages. The score at time t becomes then the average of all received reports within the time window length. Here we consider W minutes, so between 5 and 15 minutes. And the numbers here, the numbers that are shown here are also given in minutes. The final decision that is taken is based on a score threshold. And our target is to minimize false alarms. They would be very disturbing. So we set the threshold at the lowest level that we observed across all randomly selected aircraft tracks at a given time after the attack has started for our set that we consider. As a result, we achieve a false positive rate of 0% by design with respect to the considered tracks. That's specific to the data that we used as input. Overall, however, we achieve good attack detection rates for a varying set of windows and for a varying set of detection delays in a couple of minutes' time. When we depict the average trust scores, this picture here demonstrates that once we start the attack, after a couple of minutes, we are able to observe the attack is happening. So we receive noticeable detection rates here after a few minutes of elapsed time. Obviously, the higher the deviation from the correct airport track, the faster we are able to detect the attacks. But we are also able to observe it with just a deviation of 1% from the aircraft track. So much about GPS spoofing detection. Regarding ADSB spoofing detection, we consider the three different scenarios of a single receiver, of multiple receivers, and all receivers within a geographical area that are impacted by the attacks. And as it turns out, we see that the attack score drops immediately after the attack starts, as soon as the attack starts, as opposed to the GPS spoofing case. And as it turns out, the number of affected sensors is best from the attacker's point of view if multiple sensors, but not all, are impacted by the attack. So that's the favorable attacker strategy. Additionally, to identifying attacks, we also considered an identification of the type of attack that is happening. That means we transformed the binary classification of the attack detection into a multi-class classification that decides on the type of attack happening. Considering aircraft tracks without any attack modifications applied, the combined classifier yielded no misclassification. So we see 100% prediction accuracy for normal operations. The majority of attacks were also correctly assigned and correctly classified, even though there were some cases where misclassifications happened based on the type of attacks. That's subject to future work, how we can further make this perform better. For ADSB spoofing, it turned out that the true positive rate, that means the detection rate, was higher than for GPS spoofing, but this will also depend on the selected parameters and may depend on the data set. Let me add a few further observations and lessons learned. We had to deal with huge data sets. So we used data sets of 24 hours for actually 2 different days to also investigate the impact of time and the impact of weather conditions, for example. And 1 day of data in pre-pandemic flight times is more than 130 million messages that have to be dealt with, that amount to more than 200 gigabytes of data. We were able, luckily, to use standard machine learning techniques and could focus on simple decision trees for our analyses. As it turned out, these simple models fit well to our basic binary classification problem, and they were the most plausible technique to be used on our data to actually obtain promising performance and accuracy results. Finally, the source code that we have developed within this project is made available under the given GitHub link here. With this, I would like to conclude. We have worked with real-world data to explore the concept of wireless witnessing in the aviation security context, and we have received promising results for attack detection with even simple machine learning-based algorithms. I would like to thank you for your attention. We're looking forward to receiving questions and further interactions with you. And on a separate note, let me make another remark. If you are working on similar topics right now, then do consider submitting to ACM WiseTech this year. Thank you.